bring it out today because it's sort of an Excel-based assignment, and we're going to get into how to do these things in today's lecture. So if you'd like to follow along with that and make notes, or even work along with us as we get in the lecture, this way you kind of know what's coming up and what's due Sunday, so you kind of keep track of when to pay attention and when to doze off. So today we've shifted from causal loop diagrams into what I'm calling the numerical simulation of dynamical systems. And so there's this like fuzzy shape behind here, and this is kind of meant to be figurative here in that this is the beginning of our introduction to dynamical systems, and it's kind of the tip of the iceberg. It's only sort of showing us a little bit that's there towards what's the blurry image behind here is something called a strange attractor, and we'll talk about what those are in the last section. In the last section of the course. And so when we get to chaos and things like that, we'll get up to there. So right now we're sort of just at the beginning here of defining what it means to be dynamical and how to then build sims of these dynamical systems. So when I say dynamic, what I mean is we've already seen that causal loop diagrams have certain behavior over time associated with them. Now at this point, they've just been these cartoon graphics. And supposedly they can help us deal with things like this puzzling effect of say, well, you might, tolerable level of drug-related crime might be down here, but the reported level is growing. And so we have this puzzling behavior over time we're trying to deal with. Or, for example, trying to understand fishery dynamics, how you get a rapid rise in the growth of a fishery and then suddenly it slows down. And so so far we've qualitatively given descriptions of what causal loops might be involved, but we don't actually have a mechanism that helps us simulate these things outside of just looking for cartoons associated with each one of these things. And so that's what we're building now. We're finally to the point where you're going to put together systems and then hit play and then have them behave over time. And then that way you can experiment with those behaviors over time. So when I say dynamic, what I'm referring to is the dynamics, which are the forces or properties that stimulate growth, development, or change within a system or process. So dynamics refer to not only that something's changing over time, but that we're actually modeling the things that are causing them to change over time. And that's where these intersect with those causal loop diagrams. So we are building dynamical system models, which means we're building models of the things that force a system to change over time. So that's where we're kind of going with this. And there's two perspectives we can take from a kind of mathematical point of view, and we'll find that one of them, I think, ends up being easier is a more interesting explanatory tool, and is actually easier for us to implement in these modeling tools that we'll learn to use. So the first one, when we talk about like this sine wave, usually if you see a sine wave like this in a math class, somebody will put up an expression like this one. And maybe in a physics class, you might learn that there's certain properties here of the amplitude of the sine wave, the frequency of the sine wave, and so on. And you can read those out of this expression here, like that's the amplitude, the frequency is somehow related to 1 over 24. You can learn to read this. But if I were to ask you, the reason I give you this expression is that it allows me to ask, what is the value of this sine wave going to be at a particular time? So if I give you that expression, I can plug in a time value like 16, and that will tell me that the sine wave is going to be around minus 16 at time 16. So that is one perspective. It's like in one expression, it allows me to immediately know where the system's going to be at a particular time. Up until this point, it is my guess that this is the traditional way you're used to turning a graph like this into an expression. Is looking for an expression that directly maps for every time what the value is going to be. That is one perspective. But the perspective that we start to embrace in this class is a much more sort of calculus-based perspective. This was a perspective that Newton and Leibniz sort of came up with, where they realized that when you're watching planetary bodies circle around each other, it's less interesting to know about the circle that they trace out, and more interesting to know about the forces acting on them at every point in that circle. And it is my claim, and we're not going to, this isn't the normal framework that we're going to use in this class. Our class is going to be graphical and things like that, but this is behind the scenes what's going on. And it is my claim that this system of two differential equations, so two things you might learn about in SOS 211, the way they couple together, this is identical to this over here. It's just a different perspective. So if you were to take a sine wave like this one and take its derivative with respect to time and name that x, and then take that thing, whatever you end up with, and take its derivative with respect to time, then that would end up, the thing that you got for the x term would end up showing up in that other thing so that you could build this coupled expression. So just by taking the derivative of this thing twice and looking for patterns, you're able to then write something here, which is a framework which tells me not where the system's going to be at a particular time, but how the derivatives at any time relate to each other. And so this shows me that what I'm actually seeing here is a feedback loop. There are two variables, which I might call x and y, and these two variables, x and y, interact in a negative feedback loop. So I can see that as the derivative of y is equal to x, so if x increases, so does y, but the derivative of x is equal to negative something times y. So as y increases, x decreases. So by spreading things out this way and finding a way to call something x and y in here, then I'm able to sort of see that those two things that I've pulled out of this graph, x and y, not only relate to each other, but they relate to each other in a negative feedback loop. And so it turns out that every sine wave behind the scenes is a negative feedback loop between two variables that are constantly tugging on each other. One that's moving out, the other one that's tugging it back, and those two things end up moving in something we call quadrature, and then that ends up creating this wave here. This is a little abstract at the moment, and that's okay. I'm not expecting it to make total sense here, but I'm saying that we're starting in this perspective, and we're moving to the perspective where when you look at a behavior over time plot, I want you to want to see this perspective, which will be the stock and flow perspective. Even though right now, I think when you look at this, you have a tendency to see this perspective. This perspective allows you to map from one time to one value. This perspective makes it impossible, or it's possible, but it's very difficult to see how things map from one time to one value. But at every time, it gives you an impression that there are two things acting on each other in a negative feedback way. And that's what's interesting to us. It captures the systems level perspective. So let's unpack that a little bit. So let's consider the bank. So this is a compound interest example. How many people know what I mean by compound interest? All right, so basic idea, I put money in the bank. It's going to make a little money over a year of being there. Maybe every month it gets compounded, maybe every day gets compounded, and then you have more money in the bank. That more money in the bank is going to get compounded, and this thing's going to grow and grow and grow until, so even though you're not putting money in, the money seems to have a life of its own. So I have an initial deposit, $10, and let's say it's in a really nice bank account with a 20% interest, compounded annually. So every year, we look at how much money's in the bank, and we add to it. Now, when you learn about compound interest, let's say in a basic finance course, usually people give you an expression like this, the compound interest formula. Or some people might call this the F over P formula, the future over present. If I know what my present value is, I can figure out what my future value is. Or maybe you've heard about net present value and NPV calculation. So maybe in some of your courses you've heard about that, but if you unpack all of them, they end up looking like an expression like this, where you can read this expression. If you know how to read it, you see that you've got your initial deposit first, you've got this 1 that shows up under the parentheses, your interest rate, which shows up here, and then how many compounding periods out you want to predict what your money's value is going to be. So if you set this thing equal to 0, it gives you how much money you put in. That's 0. I put $10 in. A year later, I can put a 1 in here, and I end up getting 20% more. So now I'm up to $12. A year later, I get up to whatever 1.2 times that is, and this thing grows. So if you want to know how much money I'm going to have in 20 years, I just look up this expression, and I put a 20 there, and it tells me instantaneously how much money I get in 20 years. And that's the so-called compound interest formula. So that is one perspective in understanding the bank here. Now, I can give you this formula, and you might forget how compound interest works, but you at least know you can plug a value into that formula and find out where your money is. We want to try to come up with a different perspective that helps us unpack how compound interest works and model that year-to-year process as opposed to modeling this kind of projection where we don't really know what's going on underneath, but we have a formula which tells us where things are going to be. So how do we do that? Is this the best representation of the year-to-year? Well, if you think about the process, so now this is very process-centric. I dump in a certain initial deposit, and then I calculate yearly interest after, say, a year, and that's 20% yearly interest there. So I know that if I increase my initial deposit, I'm going to increase my interest. So if I have a balance, if I call this a variable in a causal loop diagram, then I know that if I increase my balance, I'm going to increase my interest. So I've got a simple causal loop there, and that is reflected here through this expression right here. So this expression has got a balance, and I can see that the balance is related to interest with a positive number in between them. So if I increase my balance, I'm going to increase my interest. And that's all that I'm showing right here. So then, I think, all right, next year, I'm going to take my old balance, and I'm going to add that interest, and that will go into my new balance, not the tennis shoe, but the bank account. And then that will then iterate so that next year's balance will be larger. And so if I increase my interest, I'm going to increase my balance. And so that suggests another causal loop. So by looking at these two expressions, this expression over here shows me that if I increase the thing on the right, I'm getting an increase in the thing on the left. This expression over here shows that if I increase the thing on the right, I'm going to get an increase in the thing on the left. This expression is the bottom positively. This expression is the top positively. I've now closed that loop, and what type of loop is that? Is this a positive feedback or a negative feedback? It's a positive feedback because there is an even number, i.e. 0, negative links. So this right here is a reinforcing growth loop, which makes sense because we know that our bank account is going to grow. But now we haven't used the compound interest formula in order to predict that we're going to get growth. We have used the year-to-year formulas of how to calculate interest and how to calculate the next year's balance. And by looking at the year-to-year processes, we can then figure out that we have a positive feedback loop and then figure out that we're going to get growth. Now, it's going to be very difficult for us to figure out exactly how much growth we're going to get in 10 years because we're going to have to go through this process 10 times. We're going to have to simulate the bank account in order to get there. But we at least have a better understanding of how the bank works. So this perspective is a much more sort of process level perspective as opposed to kind of the full perspective where we just get a formula but we don't know how it works. So we end up getting the same growth out if we simulate. So we put in $10 into this expression here. Then we can see that the next year we're going to get $12. So then we put 12 in. We see the next year we're going to get whatever, 14 some. And so we end up getting the exact same curve we got out of the compound interest formula. But in order for me to figure out how much money I'm going to get, over here, I have to go through this step by step by step by step. And that's what the computer is going to do when we end up putting in our systems. We're going to give it the kind of year-to-year perspective for our systems and let the computer do the iterating from period to period to period. And it's going to figure out what this curve is going to be. And what's nice about this is we don't actually need to know what the actual expression for this curve is. All we need to be able to capture in arithmetic, basic arithmetic, is how things relate from one compounding period to the next. And as long as you can do the basic arithmetic, you're not going to need any of the calculus. The computer is going to kind of do the calculus for you. So that's kind of where we're going here. So we captured the year-to-year forces and used an iterative procedure to then give us the compound interest formula without even knowing the compound interest formula. And that's the magic of this. We simulated the process and ended up getting out that which we could have just looked up in a book, but we didn't have to look it up in a book because we could just put the processes into the computer and let the computer go. So that's kind of where we're going. So if I kind of view this from a stock and flow perspective, you can think that I have a stock of dollars in my bank balance, and we're going to introduce this term more formally as I go on in a couple slides here, but you can kind of think that that dollar is sort of dumping in new dollars, and it's sort of growing up to almost a full dollar, but every year it only gets like 20 cents per dollar dumped back into the stock. But you don't get to actually commit that into the new stock until the next year. And then in the next year, you have now your original stock up top there, plus the new contribution to the stock. Both of them end up pouring out a new flow of new dollars, that's the interest rate. And then the next year, all of those get added to the stock. And then they end up having their own flows. And this is what is sort of going on as we end up building out that graph where we started with 10, and we go to 12, we go to 14. This is our initial $10. There's the additional 12, so now we're starting with 12. Here's the new 14, and so on and so forth. And so this is our kind of stock and flow perspective, where we have a stock of dollars, and the dollars keep sort of generating a flow of new dollars that we end up getting to put into the balance after a year's time. And so that ends up getting us this graph where we start with 10, we get to 12, and then we go to 1440. So that's what the computer is going to do for us. All we have to specify is how you get from the current stock to the next flow. And that's what we're going to do inside Vensim, inside Baker, and today inside Excel. All right, so how do we do that in Excel? If you were to simulate a bank inside Excel, then you might set up a spreadsheet like this one. And so this spreadsheet, I've got 3 columns, and I created at the top a parameter I'm calling interest rate. And I just set it to 20% up here. And then down here, I said I care about 6 years. So I'm going to put 6 years down one column. And in this first one, I put my initial balance. And so these are kind of the 2 major parameters to put in, the interest rate, the initial balance. And then all I need to figure out is how much interest is earned during that year, which is just whatever the balance is times that interest rate. So notice I put these 2 dollar signs. Does anybody remember what these dollar signs mean in Excel? For those of you Excel experts out there? Yeah.
It means to fix it so it doesn't change.
Fix it so that, I like your answer, but what do you mean by doesn't change? Doesn't change when what?
As you go to the next year.
Right, so what we're going to see here in a second is I am going to fill this down, this formula down, and by putting the dollar signs there, what that says is I'm moving from row to row to row. I don't want the formula that I put in here to change its number of rows. So notice this is in row 4, and so this is saying B4 here is referring to column B, cell 4. If I were to pull this down, it would copy the formula here, and it would change the B4 to a B5. Because it says that, okay, you copied down, and I recognize that you set a 4 in row 4. Well, now you're in row 5, so I'm going to change all of the 4s to 5. I'm going to increase them in the same amount that you increase the rows. But the $1 here tells it that I actually want this to be 1 everywhere, even if I copy down. And so that's why I've got this one here, because I want that interest rate to stay, even as I copy this thing down. And so that's what we'll see here in this next step. So the last formula I have to put in is the formula that says take the balance from the cell above and add the interest from the cell above. And with those 2 formulas, calculating interest here and calculating the new balance there, then I can end up simulating my bank account out for as many years as I want. And I'm just going to do that by taking these 2 formulas and filling them down. So in Excel, there'll be a little square that shows up here or here. You can grab that square and pull it down, and it will just copy this formula, changing the numbers in the same amount that you're displacing. So this B4C4 will turn into a B5C5, B6C6, and so on. And so if I fill down that way, then I end up getting all my balances, my initial balance, my balance of the first year, second year, third year, and so on, and the interest calculated every year. And that's using this little square that I pulled down here. And so that's how I simulate a bank. I only specified how I get from one year to the next, and then using those formulas, I copied those formulas across as many years as I wanted. And that simulated the same process, and I got what I get out is exactly what I get out of that compound interest formula, but I didn't use the compound interest formula. I used this year-to-year perspective. And the benefit of that is I know how things work from year to year, but I might not understand how that compound interest formula works. It's easier for me to explain to you if you have a certain amount in the bank now, that you're going to get 20% interest that year, and those two things are going to add together the next year. That's easy to explain. It's hard to explain where you get the initial balance times 1 plus interest rate to the k. So if you have a hard time sort of thinking through where that exponent stuff comes from, this perspective is actually, I think, a little simpler. The only downside is the way to project forward 100 years is that you have to drag down 100 rows in order to get your simulated bank balance, as opposed to the other formula where you just plug in 100 and it will give it to you like that. So that's the difference in these two perspectives. They're kind of complementary perspectives. This one focuses on year to year, but forces you to simulate year to year to year to year to get a result. The other one focuses on the global result and allows you to very quickly get an answer, but you don't kind of know what happens from year to year to year. And that's just two perspectives on a bank account. And now I'm going to translate that and how you'd simulate a more generic system like the ones that we'll simulate in this class. But are there any questions? This is sort of the fundamentals. I want to make sure that everybody feels comfortable with simulating their bank account balance in Excel using these interest formulas like this. So, because that's kind of where, this is our foundation for the harder stuff. So I want to make sure that we get this down first. So are there any questions about this basic idea? Simulating bank interest from year to year. Yeah?
I thought the main formula, you put it in the top window of Excel, or is that not?
Oh, so yeah, so I kind of simplified here. It turns out that if I were to click on this cell, up top there'd be a row up there that would also have this in it. And so you could either type down here or up there.
And in the top cell, is that where we put the fixed variable with the dollar sign?
The reason I use the dollar signs here is because I put this one here. You could put these fixed parameters, be it interest rate or whatever else you wanted to be another parameter, you could put anywhere you wanted. You don't want to put them kind of in the way of the things you're going to fill down. But then wherever you put them, you just put whatever that cell is. And if you do the dollar signs there, that'll ensure that as you're dragging the formulas around, it won't touch this one. It'll always keep the coordinates that were the same. Other questions about this? Okay. So we're using Excel for now, and it's going to be a little tedious. But then a little later, I think this week or next lecture, we'll show how to do this in Vensim and Insight Maker. And there's a lot less bookkeeping you have to do there because they're designed to do exactly this, whereas Excel is a general purpose tool. All right, so we fill the formulas down, we get the growth rate. So the basic formula here for kind of stocks, this kind of stock and flow like, bank account like system is I can set up time steps down one column, and then I create stocks. So in this case, my stock was my bank balance. And then my stock variables, I call them stocks because they're the things that are accumulating over time. So the formulas for the next stock are always going to look like the previous stock plus some formula. So then I've got these converter variables, which are like my interest calculations. And so converters aren't anything special. I mean, you might name them something to help you reason about what's going on, but they're just there to help you do the math. So I have bank balance is what I call a stock, and then the interest I could call a converter. I think that's the language that a lot of these stock and flow texts use for that. And I use the stocks and the converters to generate the flows, which allow me to move from one stock to the next. And so that will become more clear as we go on here, but basically the formula for every stock is going to take the expression of the previous stock plus some formula that comes from the previous rows, stock and converters, and that plus portion is going to be related to this thing we call a flow. So the flows are like the derivatives in that calculus example. They're the things that make stocks change. And the stocks are the things that are changing. So that's kind of the terminology. And that'll become more concrete, I think, in this next example. So I want to go from the bank account, where I know how to simulate a bank account, and I want to go to the bacterial example. So I know that dollars in the bank grow, and I know that bacteria grow. So given that I've got growth here, I'd like to say, is there a way I can use the same framework that I used to make the dollars grow here and actually end up simulating a system that represents the way bacteria might grow here? So the question might be, how do I make that analogy here? So if I know that bacteria reproduce through, let's say they're clonal bacteria, they reproduce just by duplicating themselves. Then if I think about how do dollar bills reproduce? Well, they reproduce through their interest. So each dollar bill produces a little interest. It's like producing a tiny bacteria. And once you have enough tiny bacteria, they group together and they make a whole new dollar. So somehow there should be a way to come up with a way to define an interest rate in terms of bacteria so that these bacteria can be viewed as a bank account. And then with my simple bank account spreadsheet, I can end up experimenting with different population trajectories in this bacterial growth example. That's where we're going with this example. So we got the bacteria here. And if we think about it, what are the problems with this analogy? For one, bacteria don't compound every year. There's no compounding periods. The bacteria are just growing. They produce themselves after an average waiting time of W. So some bacteria are going to spend longer than W before they pop out a new bacteria. Some bacteria will be shorter to them. But on average, it's going to take about W, and it's almost like each dollar bill just waits that amount of time until it pops out a fully formed dollar bill. Likewise, those bacteria are not synchronously popping out these new copies. Some bacteria are going to pop out a new one, but then they might be totally silent as another bacteria pops out a new one. And so they don't have the synchronized compounding like we do in the bank. And then each bacteria produces a full copy of itself. So we have to say, how do we approximate? How do we model? Remember, models aren't meant to be 100% accurate. They're meant to be useful. So how do we come up with an approximation of bacteria that looks more like a bank account? Because I know how to simulate a bank account. And the thing is, well, what if each bacteria, instead of waiting for W time and then popping out a fully formed bacteria, what if I view every bacteria as oozing out a little bit of bacteria at a slow rate that is related to 1 divided by this duplication time? So the thought here is that if I wait a full duplication time, I will have accumulated a full new bacteria. So instead of thinking one bacteria sits there alone, and then suddenly after W time there's 2, I think of one bacteria is gradually oozing out a little bit more, just like in that picture of a dollar bill oozing out a little bit of a partial dollar bill. And then after a certain amount of time, it's oozed out enough bacteria for there to be 2 bacteria. And that's what we're sort of picturing here. So we're using, instead of continuous reproduction, where each bacteria is continuously reproducing asynchronously, we're going to pretend also that all of the bacteria are synchronized in their oozing out period, so that every small compounding period that I'm going to call DT, so this was a year at the bank, but I'm just going to arbitrarily call it DT here. So I'm saying that for every DT time period, all of the bacteria are oozing out this small flow of new bacteria, and then at the end of my DT compounding period, I pool together everything they've oozed out and add them back to the population, and then let that new population ooze out for another DT time period. So I'm creating a compounding interest period that is artificial, but my claim is that if I make this compounding period small enough, this will actually be a good approximation of what is happening on average with the bacteria. So in this perspective, the interest rate is the compounding rate divided by the doubling time of the bacteria. So before, we had an interest rate of 20%. Well, now we have an interest rate of whatever this time is divided by whatever this time is. So it still ends up being a percentage. And we really need this number to be close to 0, so a very small interest rate, in order for this approximation to be close to what's actually happening in the bacteria. So, but with this framework, we can now simulate the bacteria as a bank. So we're gonna have a couple of different bites at this apple. So let's just marinate in that, and then as we go, hopefully this becomes a little more clear. So here this is in a different framework, or a different way to say it. So before, one bacteria waits W time and becomes 2 bacteria. That's difficult for us to simulate. So we are instead going to approximate it as if one bacteria, just like that dollar bill example, is always pouring out a little bit of new bacteria, and it's filling up a new bacterial compartment at a rate of 1 divided by W, where W is the time you usually have to wait to get a fully formed bacteria. And the elegance of that assumption is that if you wait the full W time, you do get 2 new bacteria. You get 1 new bacteria and 1 old bacteria. So if you just jumped ahead W, it would look identical. It would look like, oh, I waited W and suddenly I got 2. Well, here I waited W and got 2. What's tricky is that if you wait half a W, in this system, you still only have 1 bacteria. But in this system, you have 1.5 bacteria. So you wait, instead of waiting a full W, what we're going to do is wait for a tiny little DT compounding period, that's DT, so that this 1 bacteria is only going to contribute a tiny little bit of new bacteria. And then after that DT time period, we're going to combine all the new bacteria with all the old bacteria, and then let them all start this process over again. And that is going to be our bank approximation of bacterial growth. Question?
Why do we only want a small part of it to the top?
Excellent question. So the thought here is that if I make my compounding period large, so that I produce a lot of new bacteria during the compounding period, then I'm going to have a bunch of bacteria that in real life, like in the real situation up here, would have started reproducing on their own. So I need to, this approximation only works if I sort of just jump ahead a little bit in time, where I only get a tiny little bit of extra bacteria in that compounding period. So that, because once I get to the end of the compounding period, I restart the process, and this tiny little bacteria can start reproducing herself. So the point is that during the compounding period, only the things on this side can reproduce. So as we start adding, this one, as it accumulates, is not reproducing. So in order for us to better approximate what's up here, we need to keep this growth very low, and then it grows a little bit, move it over, allow it to start growing. Move it over. Excellent question. Any other questions about this basic conceptual framework for how we're turning bacterial growth into a bank account? And the hope is if we do this right, the formulas will be pretty easy to put into that spreadsheet. So we need this to be small. We need the DT period to be smaller than W. What is this going to mean for your non-bacterial growth examples? That means that you're going to have to find the time scale of whatever whatever interesting part of your system you're focusing on, sort of the fastest thing that happens in the system, and make sure that the artificial compounding period you put in your Excel spreadsheet is much lower than that. So that's kind of the key to making these discrete time simulations work, is that you have to make sure that your discrete time, your DT, your tiny little DT time unit is smaller, so it happens at a much smaller time scale than the fastest thing that happens in your system. So if you know that you're simulating the growth of a phoenix, and you're talking about population growth, well, you know that it takes a certain amount of time for humans to produce new humans. And so you probably don't need to set your simulation time period every second, but maybe you do need to set it to every day, because every day it's very likely that you'll have new people born in Phoenix. But every second, you probably can get away with saying, well, I'm going to spread, if somebody does get born this second, they probably won't get born next second, so I can spread that thing out over a day. But if I go to like a year, if I assume that everyone born in 1 year doesn't get a chance to add to the population until the next year, then I might be missing out on important dynamics. So you have to look for the fastest thing that happens in your system and make this dt faster than that. And this will become more concrete as we go on. So I just now taken the bank example, but now it's the bacteria example. I have a stock of bacteria, and now I have this thing that I'm calling a flow. And that flow is this doubling rate, the reciprocal of this doubling rate per bacteria. And my interest is going to be my flow times my time interval. In my bank account, my time interval was 1. It was 1 year. So this interest rate just looked like 20%. But it was really like 20% times 1 year, but the 1 year was kind of hidden there. So the flow is this flow rate out of each individual. And if I multiply that by the time interval, that gives me my generated interest. So I know my formula is just going to be, for my next stock, is just going to be this stock plus this interest. And so that's what I get here, is that the next stock, the next bank balance, and the next year, so each dt you can think of as like a year in the bank, is going to be my previous balance plus the interest. And in this version, both of these start contributing. And so this partial bacteria starts producing more partial bacteria. And so it doesn't look realistic because I've got a partial bacteria that's producing partial bacteria. But on average, the dynamics of the population will be very close to the real dynamics of the population. And so we just keep doing that over and over again. We have a stock, we calculate an interest, and that interest is going to be the flows times the time interval, and that generates an interest, which we add. So those two end up adding as interest to become new stock, and that gets added again, and so on and so forth. And we can simulate this thing through just like we did before. We start with one bacteria over a small time interval dt. So then after that time interval, we get the original one bacteria plus a little fractional bacteria. That's going to be 1 over W, that's how much was pouring out of the one bacteria, times the tiny interval that was pouring out on. So that's the increase in that population. But now both of these start pouring out simultaneously. And then that provides new bacteria from both the original bacteria and the fractional bacteria. And that's how we get growth. Exactly the same way we had growth in the bank account. So we just generated sort of a fictitious interest rate, and we can simulate that over a huge number of intervals, and we get this exponential growth curve, which is what we kind of expected if you have bacteria without any limitations, just growing exponentially. Now, this is where the calculus is going to come into play. If the dt is very small, then we get a very large number of compounding periods. So that's a downside of having the dt very small. But if the dt is very small, then it comes closer and closer to approximating a smooth differential equation. So if I zoom in on what's going on in the dt, I have my stock way over here at the early time, and then I have my stock plus the interest at the late time. And if I connect them with a straight line, the slope of that line is equal to the derivative of the stock formula. So if I had a formula for stock, and I took the derivative of that formula with respect to dt, then I would actually get something that was equal to this slope. So if you remember in calculus, you sort of said that if I've got a formula like if I've got not a laser pointer, if I've got a formula like f of t, then f of t plus some dt minus f of t divided by that dt, this is basically the slope of this. So if f is equal to the stock, so this down here, this here is my f of t, then this formula up here might be something you remember from calculus as the thing that defines a derivative as the dt becomes very, very tiny. And so as dt goes to 0, then you end up, this thing ends up being equivalent to the derivative of df dt, or f prime, or whatever your notation might be. And so when I say we want our dt small, what I'm really saying is that we want our bank account to be approximating calculus. is that by making the dt really, really small, what I've done is I found a way to perform integration, to get to sort of do anti-derivatives without actually doing it symbolically. So what happens in a derivative is you've got a particular function value, and effectively, if you have a very, very tiny dt, the next function value after dt is just going to be the derivative at this value times dt plus the original value. And that's how you get from one portion of the function to the next. And I just sort of cut to that. I said, I don't know what the derivative is, but I know how to get from one time period to the next. And I'm going to use that to approximate the derivative. And so we're not going to talk specifically about derivatives in this class. I'm not going to force you to do calculus. But whenever you write an expression for one of these flow variables, you are actually writing an expression for a derivative. The flow is meant to represent the derivative. And so if you have an expression for the derivative and you plug it into this and you make a really, really tiny dt, then the simulation you get of your system is going to be identical to what you get if you solved the equation. If you took the integral of, if I said I took the integral of this, whatever my derivative you gave me, df dt, if I took the integral of that thing from 0 to some final time, so I'll say call this final time, ft, that up there, you learn to take integrals in calculus. If I gave you a derivative and you took the integral, you'd give me a formula out. Well, that formula was like the first perspective, was like the sine wave perspective, the thing that I wrote over here. Now I'm saying I'm going to give you the derivative. Instead of asking you to solve for that formula, you're going to just plug the derivative into a spreadsheet and have the spreadsheet do it numerically for you, which basically means we don't solve it with symbols. We just make the dt so small that we approximate these jumps. We say we know where it started, we take the derivative, and we use the derivative times the interval, and that tells us the next spot it's going to be in. Then we take the derivative times the interval, and that gives us the next spot, and so on and so forth. So this is, not super important if you're not quite totally following that, but it's at least providing, I'm trying to give a little bit of the background of how this ties in, why we view this as calculus-based modeling, even though I'm not going to do anything that you were going to formally recognize. It's like, oh, I'm taking derivatives. The flow formulas we put in are effectively derivatives. Yeah, question?
Are flow and slope interchangeable?
I would say that when dt is small, then yes, then flow and slope are interchangeable. So if you have a very tiny time period between your stock value now and your stock value later, then the slope that connects them is going to be equal to the derivative of the stock. So at that point, that's why the dt has to be small. If the dt is large, then the flow formula you put into, the flow formula just tells you how to get from one period to the next. We only view the flow period as being identical, the flow being identical to the derivative if the dt is really, really small. And in your simulations, you're going to choose the dt's, and you're going to have to choose them to be small enough. You choose them to be too small, then your simulation is going to take forever to run. But if you choose them to be too large, then it's not going to look like this. It's not going to meet these assumptions. So that'll become clearer as we move on. All right, so how do we then implement this bacterial simulation model in Excel, keeping in mind this interest rate? We don't have an interest rate, but we have something that we've simulated an interest rate, and it has both of these elements here. So at the top of my Excel spreadsheet, and this is, I think, the stuff that I'm going to have you, I think the first question of what's due on Sunday is you basically replicating this. So in your own spreadsheet, build the simple population dynamics model discussed in lecture D1. That's what we're doing here. So the idea here is at the top of your spreadsheet, you've got the DT period and the W period. And I might point out that if my doubling time is 0.75 time units, so on the assignment, I keep referring to time units. If it's easier, whenever you see the two words together, time units, just think seconds. So I don't know what the time units are, but I'm saying here that it takes a bacteria 3/4 of a time unit. If it helps, just think 3/4 of a second to double. And here I'm saying I am going to simulate time steps of 1/10 of a second every time. Now this is probably not small enough for this to be a good simulation of the bacterial growth dynamics that I'm trying to approximate, because 0.1 is not that much smaller than 0.75. As we move on, we'll figure out ways to evaluate if you make good choices of the DT value. For now, I'm just gonna, because it's easy, just choose 0.1 and 0.75 for this example. So then I need to come up with my bank balance and interest rate formulas. And so my initial bank balance is the number of bacteria. Let's say I seed this with one bacteria. These are clonal bacteria. They reproduce asexually. So if I've got one, then I will eventually get two. And so the flow of new bacteria, that is going to be equal to, and this is not quite the interest rate yet, it's almost the interest rate, the number of bacteria times the flow contribution per bacteria. This is like the 1 over W that we had in the previous slides. So this is however many bacteria I have, each one of them is pouring out at this rate. So in order for me to get my interest rate, I have to multiply this thing by my DT, and that's going to show up in the next row. So in this previous row, I've got my number of bacteria, I've got the flow that is without a DT. So the flow is without DT. So flow is the derivative, there's no DT in the derivative, so it's just the amount, the rate of change due to the entire population. So in my next time step, I know I started at time 0, and I'm going to add DT to it to figure out where I'm now in my time step. So I just did my previous row plus the DT, which has just got those dollar signs in it, means it's those special parameters that's up there. So as I fill down, it doesn't ever change these. It keeps it B1. That's why the dollars are there. And then this is where the interest rate formula comes up. Notice this is the flow from the previous row, C5, times DT. So the interest rate is embedded in this formula here. I could have created another column over here called like interest rate, and it would just be whatever was in this flow cell times DT. And then I would be adding that interest rate to the previous stock. So that's all I have here. And this is always going to be the formula for these stock progressions here. It's going to be the previous stock plus DT times all the sums and differences of the flows from the previous row. So here's the DT, and there's a single inflow called C5, which is this one here. And now I have enough that I can simulate the bacterial population. So I can just fill those things down, and here's my number of bacteria as they grow, and here is the flow of new bacteria every time step as they grow. And you can see the time is moving in steps of DT, 0.1, 0.2, 0.3, and so on. And if I plot that, I've got on this, I've got all the way up from 0 to 1.3 time units. So in the exercise, I ask you to plot up to 5 time units. What I mean by that is I want you, this should go in steps of DT, and you should go all the way up to 5. So the number in this cell should be 5. It's however many rows you need to make this equal to 5. And then when you plot it, it'll go from 0 to 5, and the trajectory will do whatever it does over those 5 time units, and I get this growth here. So that's me turning bacterial growth into a bank problem and then simulating it in the exact same way I simulate interest. Are there questions about that? Any steps that you want me to go back and check on? Yeah?
I was just wondering, so if the flow is calculated by 1 over W, then what were we talking about as being DT before?
That's the interest rate. So the flow, this here is the 1 over W. It's actually 1 over W times the number of bacteria. So I'll do times number, and that number is this thing here. So I'll say number is equal to that. And then this thing here is DT divided by W times the number of bacteria from the previous row. So the B1 is the DT, the C5 is the 1 over W times number. So here, there's the 1 over W times number, and then multiply it. Does that make sense?
I'm mostly just wondering, like, what's the point of separating BBT and what is it?
So why didn't I put the DT up here? Is that what you're asking? Or
Well, you said that you don't put the derivatives in. No, what is 1 over W?
right? Okay. So this 1 over W times the number of bacteria. This is the instantaneous rate of change of the population. So at any instant of time, it is how quickly the population is growing. And so it is not defined in terms of an interval. So if you were to ask me what is the state of the system, I would say the system is the current number of bacteria and how quickly the bacteria are changing. And that's all I would tell you. You'd say that there are currently 1 bacteria and they are growing at a rate of 1.33333 bacteria per second. Now, in order for me to then simulate what happens a 1/10 of a second later, I take that speed and I multiply it by this interval of 0 to 0.1. And so now you might say, wait, that's too coarse of a resolution. I want to know how many bacteria will be there in a 100th of a second, not a 1/10 of a second. In which case I would change this here, or change the dt to a 100th of a second, and then it would automatically change down here. So from a modeling perspective, dt, you don't want dt to enter your model, because it's kind of an artifact of how you do the simulation. From a modeler's perspective, all we care about is the state variables and the rates of change. But then when you actually have to do the sim, you have to make a decision of the dt. But that is sort of up to you, because it might be that when I do this plot here, if I were to change that dt to 0.01, it would look identical. It just would be more fine-grained. In which case, like, really I'm trying to capture the line here. I don't care about the choice of dt. So when you go into Vensim, Vensim explicitly, like, in fact, in order to find the dt, it's hidden behind a menu somewhere. So in Vensim, you give it the flow and you give it the stops. And then if you want to change the dt, you go somewhere totally different to find it. And that's what I'm trying to simulate or emulate here, is that we are separating out the dt from the flow. Does that answer your question?
Yeah.
To come close?
Yeah, thank you.
So
Yeah.
when we're doing this, are we just manipulating the dt that we're choosing instead of 0.1, we're choosing?
That's an excellent question. So one of the questions you have as a modeler to start with is, what is the right version of dt? And I think that's actually going to be question 3 on the assignment due Sunday, is to experiment with that. And basically my claim is that if you did this in Excel, you set this thing up, if you went up here and you changed this dt, you made it like 1, or you went and made it 0.01, 0.001, then what you would see, now you might have to be careful about adjusting the number of rows, because if you make it really, really fine, then if you only have 10 rows, you don't actually simulate that much time. But as you change this thing, you'll notice that certain values of dt will give you totally different curves. But as the dt gets smaller and smaller and smaller, eventually the curves start laying down on top of each other. And so what you'll find is there's kind of like an optimal dt. There's a dt that if I make it any smaller, I don't get any change, but I need more rows of spreadsheet. Excel needs to take more time to calculate. So I want to make my dt just small enough to reach that point, but not any smaller, because that means that like some simulations I do for like my research might take a week to complete. So, and if you view them as like the dt that I'm using, if I go from a dt of 0.01 to 0.001, that might go from a week of simulation to a month of simulation. So if I can get away with 0.01, not 0.001, I really want to go with 0.01. So that's one of the things you'll do here. Now, practically, once you've settled on your dt, you're more interested in things like what happens when I change the doubling time? What happens when if I have a death rate that's in here, which I don't currently have simulated? What happens when I change the relationship between the birth rate and the death rate? If I were to introduce something that kills the bacteria at a particular rate, how potent does it have to be for me to control the population? Those are the types of questions we'll ultimately answer. For now, that's a type of question, what's the dt? But for your stakeholders, they're not going to care about your dt is. They just hope that you picked a good one to make for this curve that they go. Does that make sense? Yeah.
You might have mentioned this, I just want to clarify though, but when we do the first question on the homework, do we change the dt and the waiting time, or do we use those two same
For that one, I'm okay for the first question. It's kind of up to you. If you would like to just leave it this way, and then that way you can see if your numbers match mine, then that's fine.
Okay.
But then I think I then ask you in the number 2, I asked you to modify it so that we had a death rate, which I think we'll get into here in a second here. And then I also then have you play with the DT. So that'll be your opportunity. But for the first one, it's just kind of stretching out in that exercise, and it's okay to leave it with these guys.
Okay, thank you.
Yeah.
And I know you just stop ranting about it, but like for the goal, the point of it is to get kind of the same kind of graph but in less of the time.
Yeah, you want DT to be as large as possible without, DT will hit a point where if you make it any smaller, this graph won't change any. And that's where you want it to be right at that cusp. Because if I make it smaller, I'm just going to use up more computational time, but I'm not going to get any improvement in the accuracy of my model.
Okay.
Yeah. All right, so let's move on here. So this is the generic framework for any stock and flow model. So you're going to start with this bacterial growth example, and then we do a different example, a negative feedback example on Thursday. And they all look like this. So this is like the generalized bank model. You've got your stock columns, which are like the bank balances. And then you've got these flows. And these flows are like, they're related to interest, but they're like interest after you divide by the compounding period. So they're like interest divided by dt. And every stock is going to, so the time column is going to be whatever the previous time column is, plus whatever your dt value is. So that's what I'm trying to simulate down here. That every variable in the time column is going to be previous time 1 plus dt. If I move over to the stocks, every stock variable is going to be the stock variable directly above it, plus dt times the sums and differences of all the flows in the previous row. So I have these flows in this row here, and so for this stock, then I would find the flows that relate to this stock. So in this case, there might be flow 1A and flow 1B. And then I would say, all right, then this stock is going to be the previous stock plus dt times, and then parentheses, flow 1A plus flow 1B. And then for stock 2, this cell would be the previous stock plus dt times flow 2. In this case, I only have one flow here. And so those flows, those actually represent the derivatives, the things, the speed, the instantaneous rate of change of all these stocks. And that's where we do a lot of our modeling. We say, given that our stocks are this particular value, how much do we expect them to be changing? And that will allow us to predict what they'll be in the next time step. And that arithmetic is what we'll learn how to do as we move forward. And then if we do need a couple of extra columns here to make that math look cleaner, we can create converter columns. So that's the generic way that we implement these things. So as an example, if I've got my bacterial column here, I already showed you how to do an inflow, but I'm also going to ask you in number 2 of this one to simulate an outflow, to simulate a death rate. And that so I've got the birth rate from all bacteria, that's going to go into one flow. That's all the 1 over W. But then the question is, how do I simulate an outflow? So a negative flow where each bacteria only survives for a certain amount of time. And that's what we'll want to put for that number 2 in this column here. And then we'll end up getting the birth rate minus the death rate, that whole quantity times dt, when you calculate the next bacteria. And then converter variables can help with that. So kind of in summary, what you're implementing now in the Excel is what you will implement in Vensim with these diagrams. So we've got stock columns. You're going to draw stock variables in Vensim or Insight Maker. You've got flow columns. You're going to draw these thick lines here. Those are the flows that you can drill down into the flows and put formulas here. And then you're going to connect the stocks to flows if you use the stock in the formula over here. And that may involve converters to make those formulas easier. So the 3 types of columns I showed you in Excel, stock, flow, and converter, are all represented graphically in Vensim here. But note that DT is not represented anywhere here, it's hidden. And inside Vensim, there'll be a special menu category where you can change the DT, but it's not actually viewed as part of the model. It's just viewed as an auxiliary to the model in order to predict where the model will be at every time step. And knowing what the right DT is going to be different for every model because some models are slower and faster than others. And so ultimately, behind the scenes, what you're actually doing is calculus. And so this diagram, I claim, is identical to these two formulas. The graphs that you get out when you plot the stocks, when you plot the bacterial growth over time, if you were to come up with a formula to express those graphs, if you were to take the derivative of that formula, you would get the formula you put into the flow. Or alternatively, if you took the formula you put into the flow and you took the integral of it, my claim is that the formula you get out would describe the trajectory you get that Vensim or Excel will plot from this process. So this is a way for us to numerically do the things that you used to do in symbols when you say took SOS to 11, when you're doing the raw calculus. So are there questions about any of this stuff? All right, so I'm going to spend the rest of the class you guys getting started on this assignment. Happy to help with that. Basic timeline going forward. You've got Vensim on your computers. You've also got Vensim you can download for free. Also, try to get an Insight Maker account set up just in case you might like Insight Maker better than Vensim for the stock and flow stuff. Start thinking about your final project teams. So this is Unit D. So after Unit D, we're going to have the midterm. And then we'll start Unit E, and I think spring break is somewhere in the middle of that too. So I think we'll do the midterm, if I remember correctly, the midterm retake, and then there's spring break, and then you come back for that, and then there's a lecture. I think E2 is the first lecture after spring break, and so I'm hoping that basically roughly a week after that, you'll have an idea of who's going to be on your team. So we want nominally 4-member teams, and to do this, and there's going to be a short Canvas assignment where you end up submitting your team names, and then about, I don't know, it's like a week or a couple weeks after that, you're going to give me kind of a paragraph on what you plan to do. So you're not going to do the model, but you're at least going to sort of tell me what's up. So, so just looking forward, start thinking about that. It's still a little too early to panic about that, but just start thinking about that. In the most immediate, we've got today's assignment. There's going to be another similar assignment coming up. And both today's assignment and that assignment, I'll give you extra time for this. So today's assignment isn't due this upcoming Sunday, or actually it is, yeah, so that would be great. So I think I had these a week off the last time. I skipped all the lectures up one this semester. So, so I'll think about, let me look at the timeline. I might adjust the due date for assignment D2, but let me look at the timeline and see how that works out with everything else. But today's assignment should be a short one, so start that today, and I'm happy to help with that. Midterm, like I said, it's coming up after lecture D4. We'll basically do lecture D4, which will be a week from Thursday. Then we'll do a review lecture, and then we'll have the first midterm. Hopefully I get the grades back with you over that weekend, and then we'll have the midterm retake. And then there's one other lecture that will be lecture E1 and then spring break. So those are coming up. And that's it. So I'll leave the attendance exercise up to here. So if you were to pick these, so my attendance question here is, of the terms stock, converter, and flow, which one of them represents the derivative of a time signal? So is it a stock, a flow, or a converter? So I just want you to pick one of those 3 words, stock, flow, or converter. Which one of them is the derivative? Okay, so the thing you already have is so you're saying that every bacteria produce birds after waiting W time period. So here I'm saying that every bacteria gives a death, so it reduces one population half the time. Probably, yes.
I told you.
Yeah, so you're not gonna add something down the road, you're actually add another control. So you already sort of have a flow corresponding to birth, and now you need a flow corresponding to death. Well, like, so yeah, flow of new bacteria, and you can think of like that could be inflow of bacteria, and then the outflow of bacteria would be, it would look just like the inflow of bacteria, but it's going to be negative. So there, the $2, $2.06, that's like the waiting time. So can you sort of adapt that logic to thinking about how much partial depth you get every So work on that, chew on that. Maybe I'll focus. So, and then a little help on number 2. So someone might ask, how do I implement this depth rate? So number 2, I say, after 3 time units, on average, every bacteria dies. Now, let me get your mic for a second. So the basic, if we go back to thinking about the spreadsheets, so if I go back to this spreadsheet here, I am not asking you to go down 3 time units and then make an edit down here. I'm asking you to add another column. We wrote the inflow column in class, and so effectively you need an outflow column. Remember, the formula for the inflow is basically the number of bacteria times the inflow rate per bacteria, which is 1 over W. So every W time, every 0.75 seconds, you get a new bacteria. What I'm telling you is every 3 seconds, every bacteria removes itself from the population. So you should be able to use the exact same logic you used here to create an outflow column here, and then you'll combine their 2 effects, one positive and one negative, in the formula you put down here. Yeah.
So do you want us to go to -0.1 on our graphs, or can we just start at 0?
No, everything starts at time 0.
Yeah, I just mean like your graph right there has a -0.1.
Oh, that's just the way Excel did the scaling.
Okay.
I'm okay if you do 0.
Okay, awesome. Thank you.
All right, so I'll walk around, but that's my hint.
That'll change the formula. Yeah, since you'll start that next row there, the minus.
Oh, once you get all the way to
Minus.
you have 50 rows or 500 rows. You have 15 there.
Yeah, this would be the number of bacteria at time 1. And then we'll just go.
If you like to plot the flow, you can. But then just make sure it's labeled which one's the flow.
Well, if you know, like, how you do the math, like, it's just the death rate, right? So it's like, you get your increase.
Okay, so if we probably your time series, your
Or no, it's the current rate
what you want like the Y data or the X data. I guess it's only plotting the Y data. Probably only plotting this. Probably highlighting down here and the chart. And so it would be, it's like, yeah, if you do both of these together, then you're plotting directly in the chart. Good job. So like, let's say, this chart.
This is your.
Well, yeah, you can right. Yeah. This is inflow, which is number of bacteria times how much they produce. And the other one
outflow. Well, yeah, but it's not gonna be 0.75, it's gonna be this. So, you kind of think of every bacteria as leaking out of the population at a slow rate of 1 over 2. We will go over it on purpose, but I'm almost positive. In fact, the lecture you're online, I'm almost positive you really want to look at it.
That's just to see it, but I was saying, that's the new number, because it's got the first, whatever bacteria was 10 zeros and then died. And then at 3.1, everything that was there.
Oh, I see. So simple variable.
Number of bacteria.
Well, so there.
No, just. Okay. There's a gap of 3 times the because if I was born at 2, I don't die until I'm 5.
Yeah. So if you're receiving your assignments back, on the key, I think I put for the one where it's single variables, the single loops, the single there are some links. Well, that's one where it said like where it's free fill in the blanks. If you put in variables on that first blank and got marked off because I was looking for links or vice versa, just give me your, I'll correct that. I can give you credit for that. So just make sure I get that before you leave.
My mom
Yeah, right. So,
Okay.
like, let me help you. Like, I can't do full time.
Welcome.
College. That taxes.
Yeah, that's better.
okay. So,
How's your house hunting going?
so the first sheet so my W is how much time I wait for every bacteria to be now I have a new way we call it lifespan. So we're saying now bacteria is going to wait so the idea is that number of bacteria so you imagine you're going to have this column, when you look at this column, W something. It's like other variables would be 3. So, and well, so the idea is that you have bacterial users, so bond is and if you fill this down, in this expression, C7, you're adding parentheses, C7 minus D7. So where the C's will be all the input, as in the D's will be all the outputs. like, so what's neat is a formula like this one. So I'm going to copy this and put it over here. Yeah, so then this.
Oh, you want my sisters though.
So right now, this is what I'm saying, inflow and outflow. If I were to fill this thing down, then inflow is all equal to outflow. So over here, if I were to say, if I were to change this C7, open parentheses, C7 minus D7, I would see no growth whatsoever because the bacteria just stay in the bubble. So the idea is that okay, like my outflow is equal to inflow. I want my outflow to be equal to something related to this death rate, where this death rate is this, I'll call it L equal to 3. So if you were to create like another parameter here, L, and then call it equal to 3, because each one moves for 3, then my is saying, can you modify this outflow expression to use that lifetime instead of that lifetime? So this is how much life a single bacteria lives until it produces a new one. This is how much life a single bacteria lives until it reduces the population.
And then, from what I understand,
So this formula is currently parameterized in terms of that lifetime. So you would change that formula to be represent, to represent how much bacteria are being lost every compound period. And so we'll go over this more, if I remember correctly, at the presentation for Thursday, on Thursday. But, so I don't want to go too far, but at least give a hint to try to think about, so just to see if you absolutely understand what's going on in that formula.
Yeah.
Okay.
because,
Well, I would say,
yeah.
think about
Because
it.
you're
I have to
adding
pack up
something here,
when
you
that
would be
person comes in.
subtracting something.
But, so give it some more
Two
thought and focus on trying to understand what's going on in this column.
Or like
And
the
once you
rate
understand
itself
what's going on in this column, then this column I think will be very easy to get.
Causes that reduction.
And we'll talk about this more as we go on.
What
Oh, I was saying that you wrote, so some people wrote, unfortunately that is not what I was looking for, but some people wrote, I was looking for links, and some people wrote variables, and variables is also a good answer, but I didn't have that.
It is on Canvas as well, but sure.
Oh, is it just the
It's just the assignment.